This is section 2 of chapter 0.5, our mini unit that comes in between chapter 0 and chapter 1. Today we're going to be solving systems of linear equations algebraically. So our last section we did it graphically. We found out that that's not always the most accurate way. So algebraically is going to provide us an opportunity to make sure we always have the exact right answer and we don't have to estimate what our answer is. All right, so there are several different ways we can solve algebraically. Let's start with substitution. Substitution is typically a method that we want to use when one of our variables is by itself or easy to get by itself. So if you look at this system right here, x doesn't have a coefficient, it has 1, but doesn't have a coefficient other than 1. So that would be the easiest variable to isolate. So we are going to start by subtracting 2y to the other side so that x is now by itself. Once we get a variable by itself, we can substitute all of what it's equivalent to into the other equation. So x comes out and 2 minus 2y goes in its place because that's what x is equal to. So essentially we now have 3. And then where the x was, we have 2 minus 2y plus 4y equals negative 4. You'll notice this equation here now doesn't have any x's in it. So we can just simplify and combine all of our like terms to solve for y. And once we solve for y, we can then use that to help us find x. So we get y equals 5. So now we can substitute 5 back in for y into either equation, doesn't matter which one. I'm going to substitute it into the second equation. X plus 2 times 5 equals 2. So we find out that x equals negative 8. So we always write our answer as a coordinate point, an ordered pair. Negative 8, 5. But you want to double check. Does negative 8, 5 actually work in both of those equations? Because what if we accidentally did some math wrong? So take 3 times negative 8, negative 24, plus 4 times 5, which is 20. Negative 24 plus 20 does equal negative 4. And then negative 8 plus 10 equals 2. Remember that this solution has to work in both of them. One of the great things about solving algebraically or solving systems in general is you can always be sure if you have the right answer or not. So when you're taking a quiz or a test, you can check all of your work before you turn it in and you'll know if you have 100% before you even turn your paper in. All right, the next method of solving algebraically is linear combination. Sometimes we call this elimination, because our goal is to eliminate a variable. In order to eliminate a variable, we need to have a variable that has the same coefficient as the variable in the opposite equation. So we need our x variables to be the same or our y variables to be the same. And personally, I like them to be opposites. So I like my x variables to be the opposite. Did I say variable? I meant coefficient. My x coefficients to be the opposite numbers, or my y coefficients to be opposite numbers. I'll show you why in a second. So I need to multiply one of these equations by something so that I can get those coefficients to be the same. To me, it looks like it'd be the easiest to multiply this top line by 2 so that they would both be 4s here. But as I mentioned a minute ago, I like them to be the opposite sign. So I'm going to multiply this top line by a negative 2. So you'll see that if I take negative 2 times 2, I get a negative 4x, which is the opposite of 4x. All right, and then I have to take the negative 2 times negative 4y, and I have to take the negative 2 times 13. So it has to be multiplied all the way through. Sometimes people forget to multiply the constant over here. So multiply all the way through. This line stays exactly the same. And the reason why I like my coefficients to be the opposites of each other is because I prefer to add rather than subtract. If they're the same sign, you have to subtract. If they're opposite signs, you get to add. And typically people make less mistakes when they're adding. So that's why I encourage addition over subtraction. All right, if we add these first two together, that's 0. So that's not there. Add these two together, we have 3y. And add these two together, negative 18. So we find out that y is negative 6. Just like with substitution, after you get the answer for y, you're going to substitute the value into one of these equations, doesn't matter which one. I'll put it into my original first equation so that we can solve for x. So we have 2x plus 24 equals 13, and 2x equals negative 11, so x equals negative 5.5. So we're going to write that as an ordered pair. Our answer, negative 5.5, negative 6. And check it in both equations. And you can use your calculator check. Take 2 times negative 5.5 minus 4 times negative 6. Make sure that equals 13. Do the same thing with the second one. 4 times negative 5.5 minus 5 times negative 6. It's got to equal 8. If it doesn't, then we did something wrong with our math, and we'll have to go back and try it again. All right, let's do another linear combination. On this one, the coefficients, currently we can't just multiply the top to become something on the bottom or multiply the bottom to become something on the top. They're not multiples of each other. So on this one, we're going to have to multiply the top and bottom by something. And there's lots of things we can multiply by. So some people just like to switch the coefficients, like multiply the top by negative 5 and the bottom by 7. Or you could make the y's the same, multiply the top by 8 and the bottom by negative 12. That would make the y's the same. I prefer to use the lowest number possible because generally I'm working without a calculator. So I'm trying to think of a number that maybe these go into. With the 12 and the 8, they both go into 24. So I can multiply the top by 2 and the bottom by 3, and I'd have 24s for both of those. Since the 12 is already negative, I'd have a negative 24 and a positive 24, which is how I like things to be opposites. Notice that this time we're getting the y coefficients the same, whereas on the last example we got the x coefficients the same. It doesn't matter which one we eliminate, but you do need to make sure you distribute those values all the way through. All right, so go ahead, hit pause, solve it all out, and then come back and see if you have the right ordered pair at the end. Although you should be able to check in both equations and know if you have the right ordered pair before you come back to the video. All right, so this first one, we have 14x minus 24y equals negative 44. Negative 15x plus 24y equals 42. Since those are opposites, we get to add. Ends up with negative x equals negative 2. So x is going to be a positive 2. We will substitute that back into either equation. I just picked the first one so that we can find y. 14 minus 12y equals negative 22. And negative 12y equals negative 36, so y equals 3. So our ordered pair, our solution would be 2, 3. And that does check out in both equations. Now, just like with graphing, there's two special cases that could happen where we don't get a standard ordered pair intersection. We could have a situation where the two lines are parallel. We saw that in the first part. And therefore, we would say no solution. Algebraically, that shows up as 0 equals any other number. And sometimes not even 0. You could possibly get something like 7 equals 12. Any statement that's not true. Same line tells us that we have infinitely many solutions, and that's when both sides equal each other. So 0 equals 0, or 2 equals 2. Something like that would be infinitely many solutions because that's always true. So let's try it out here on number 4. We'll see what happens when we solve these. You can use substitution or you can use elimination. I tend to prefer elimination, but it really doesn't matter. If you like substitution, that works well on part A. You get the x by itself and substitute it in. So just hit pause, solve it out, and then come back and check. All right, as I mentioned, I like using elimination, so I'm going to multiply this by -2. So I get -2x plus 4y equals -6. I just wrote it down here. So now when I add them together, 0 plus 0 equals 1, which obviously isn't true. So we would say no solution. So that means we know that those lines are going to be parallel to each other. Over here on part B, again, you could use substitution, although this would be a harder one to use substitution on because there aren't any variables that are currently by themselves. So I would say elimination be good on this one too. But again, we're going to have to find something to multiply by. None of these are multiples of each other, so we're going to have to multiply both lines. Let's see. We can multiply the top by -15 and bottom by 6, top by 25 and bottom by -10, just switching, but trying to use some smaller numbers. Let's see, 10 and 25 both going to 50. So I can multiply the top by 5 and the bottom by 2. So that would give me on the top 30x minus 50y equals 60. The bottom would be a -30x plus 50y equals -60. They're opposites, so I'm going to add. I get 0 plus 0 equals 0. So that would be infinitely many solutions. So just like when we're graphing, we have the same possible outcomes. We could have one solution, which is an ordered pair. We could have no solutions if the lines are parallel, which means we get an answer that doesn't equal it. And then we could have infinitely many solutions, which gives us an answer that is equal on either side.